Okay, welcome to this special session. It's really on problems from the homework. Okay, unless Byron and also Byron, I think, also sent me a message regarding this very same problem, problem 94. Is that correct?
Excuse me? Sorry,
Yeah, you asked about problem 94 from the homework?
Oh, yeah. 21.4 or 21.94. Sorry. Yeah.
Yes. Okay. How about you, Oscar? Is it the same thing? So let's get into that problem. Okay, let me open it first of all. And it's actually on the book too. So all of these problems are in the same thing too. So they should be on the same book. Hi, Drake.
Okay.
Okay, so let me get into
Hello.
my share screen. Okay, and let me open, oh man, it opened in the wrong side. Let me move it, oops, I moved. Did I lose my share? Are you guys still looking at? Are you
It's
still
still
looking
there.
at the one? Note good, because I moved something and the other one moved and things like that. So, okay. Problem 94, that's the first one. So basically it has an insulating rigid rod of length 2A. Negligible mass is attached at its center. Let me look at the book in here because it's probably easier to read it off of the book than reading it from the chapter 21. That's problem 94, which is immediately before the problem that we did in class last time, which is problem 96. What is my marker in here? So what we have in here, we have an insulating rigid rod of length 2A and negligible mass is attached at its center to a pivot point at the origin and is free to rotate in the XY plane. A small ball with mass M and charge Q is attached to one end of the rod. A second small ball with mass M and no charge is attached to the other end. So basically we have a rod and two masses on each end, okay, on the rod. And the rod can spin basically around the origin, around the axis passing from the origin on the XY plane. So basically the axis of rotation must be the Z axis then. If we're going to choose the XY plane for the rotation, then the Z axis must pass through the origin then in this case. And what else does it say? A constant electric field E is equal to, I need to start writing in here. E is equal to minus EI, I hat, okay? So it's a vector that is minus E 1, 0, 0. I'm gonna write the 3D notations because I noticed when I was reading the problem that we're gonna be dealing with torque. And if I'm gonna deal with torque, so I better probably, it's much easier since I'm given components to use the expression, which is R cross F, and use the vector representation of this cross product. Do you guys remember this expression from physics 4A?
A little. Yeah, when I was going into this problem, I initially didn't recognize torque, so I had to look back on it.
This is from physics 4A, basically the torque in magnitude is equal to the R times the force times the sine of the angle between the force and the vector and basically the point of application of the force. So here is basically from physics 4A. So you have an origin somewhere and you have a force that is applied at this point. So this is the R vector and there is a force in here. So the torque in this case is given by if this is angle theta, is given by R, the magnitude of R times F times sine of theta, or sine in this notation of the angle between R and F. So this is basically in a nutshell the notation for it. So that's the torque. But the direction of the torque is given by the right-hand rule though, if we're going to use this formula, the second one. So in other words, if this is R, if this is F, the torque then is perpendicular to both R and F, okay? But it's much easier, as a matter of fact, for this problem not to use the right-hand rule and basically twist and torque and all of that. So what we're going to do is we're going to use the algebra to get the value for this. We're going to basically blindfold our eyes and use algebra to find the force. We already, I mean the torque. We already found the E, the electric field. It's given actually as being minus EI, I hat. And the vector I hat is in the X direction and has zero components both in the Y and the Z direction. Okay. Is this okay so far, this notation?
Yeah. So far, I understand it.
Okay, so good. So then we can move on with the problem, because at this point I didn't draw anything about the problem. I know that there is a rod that can spin in the X and Y plane. Perpendicular, right. Basically the plane is actually where all of the action is happening. So the axis of rotation must be in the Z direction. Okay. Mm-hmm. And it has two masses. It's negligible mass. Does it say negligible mass? We gave us its length. Yeah, negligible mass. So the rod doesn't have any inertia. So we don't care about it.
Oh, okay.
So the only thing that is of importance is the mass in here that are attached to its ends. One of them is charged, the other one is not charged. So the one that has a charge Q should be already under a force that is equal to QE. So that force we know already because of the expression above. Multiply this by E, so the force we know its value already. So it's minus Q times E, and it's in the X direction also, pointing in the negative direction. Because Q and E is given, EI hat, all I did was multiplied by the charge Q. The other one has no force on it, zero force, end of the story. Okay. And is present in the region Y greater than 0. So this electric field has a property that it is 0, that it is true only for Y greater than 0, but for Y equal or less than 0, E is 0. So that means this force only exists in the upper side of the plane. Okay, there is no force in the lower plane because there is no electric field in the bottom. Does this make sense? This is basically what I'm trying. I'm trying to read the problem. So when I'm solving problems, I try to read them and see they make sense to me as I'm reading them and translating them into mathematical expressions so that I can solve. Mm-hmm. This is the plan. Okay. So as a vanishing electric field, define R as a vector that points from the center of the rod to the charged end of the rod, and theta as the angle between R and the x-axis. So this is basically using polar coordinates, that's all. Okay. Let's see how that looks. The direction of the increasing theta, the direction is oriented so that theta is equal to 0 and is given an infinitesimal nudge in the direction of increasing theta. So basically, let me draw the axis now, so we are empowered with more information. So here is the x-axis. Here is the y-axis. If you're wondering what happened to the z-axis, it's coming out of the surface, okay? Because this is xy, so the x-axis, the z-axis is pointing out, okay? So that is the z-axis, this is the x-axis, and this is the y-axis. The electric field in here everywhere is equal to minus E in the I hat direction, so it's pointing this way. And here E is equal to 0. So this one is equal to negative EI hat, because this is I hat. This is J hat. And K hat is coming out. Does the picture make sense to you guys, at least so far?
Yes, that helped out.
Yeah.
Okay. So initially they said theta is equal to 0. So the rod initially was here, but then the rod now is spun a little bit so that it's actually making an angle theta. So this is the rod, the actual rod, and it has like a dumbbell basically. It has a mass in here M, and it has a mass in here M. This one is where the Q is. They said the one with the Q is the one that has the angle theta. So this is the angle theta. So if you're curious trying to find which way the force is going to be pointing, the force also points in the same direction in here as the electric field. So this is the force F equals to QE, or minus QE I hat. So far so good, yes?
That makes a lot more sense now. See, I didn't realize that what's it called? The electric force was moving it that way towards the x and how it was at an angle already. So in my
Yeah.
head, it was as if almost if it was flat or perpendicular to the x coordinate. So it just kind of didn't click until you kind of drew it out.
Yeah,
So
actually,
that really helps.
yeah, from the lecture, we saw that the force is always equal to the charge times the electric field.
Mhm.
Okay? But the only thing in here that is given to me is the electric field is given this specific direction. It's negative EI hat in y greater than 0. When y is less than 0, there is no electric field.
Right.
So on the bottom, if this path was to move all the way to the bottom, it will not find any electric field in there. So there is no force in there.
Okay.
Okay?
Yeah.
So far, so good.
Mm-hmm.
What's the first question? Okay. Write an expression for the vector. So this is R, by the way. They said use this as a vector R. The length of this vector is A, actually, because this has 2A in length. So A is here and A is here. So R must be the length of R, okay? Is A exactly, correct?
Right.
And they want us to write, but its direction is theta. So the direction of R is exactly theta. In other words, the angle R makes with the x-axis is theta. So initially they said it was at theta equal to 0, and then we moved it because they defined theta as exactly the angle with the x-axis. So we're following their notation now. Is everybody with me so far? I know we have, how many people are here?
What is that little symbol next to the R?
That's the angle, the symbol for the angle, the direction.
Okay.
That's my notation. I mean, if you did 4A with me, I didn't teach 4A at all in Riverside at all. I used to teach it until I memorized it and get sick and tired of it, so I don't do it anymore. Okay. But I can do it actually, and that's the symbol I use for the angle. Basically, like an angle with the angle symbol in it. Okay, so read it as direction.
Okay.
Of R. Okay, that's just a notation. Okay, so far so good. Is Marcella good with me? Everybody in here who is present is good so far? Following?
I don't know what problem we're working on because I was like 2 minutes late.
Okay, we're doing problem 94, which is the first problem, and apparently it's the most one that gave headache to everybody because I just saw the score in one of the classes and it's not doing well at all. So I'm going to adjust the grades for that.
94 on mastering chemistry?
Mastering physics.
Oh, I'm sorry. I'm trying to do chemistry and physics. I have lecture the same day as yours, so I'm like, I was just getting out of chem. But yes, mastering physics.
Yeah, who's your chemistry? Is it Tyler, one of the Tylers, or is somebody else?
No, I'm taking Lugo.
Okay, I don't know.
Yeah.
I'm new to campus, so I don't know much about the only two people I know are the two Tylers.
Yeah,
one of them actually.
I'm taking Lugo.
Okay. So far, basically it's problem 94, and Marcella and anybody who came in late, we're trying to set it up. So what we said in the problem is the way that it was stated to us. They told us that there is basically a rod of negligible mass of length 2a, and they attach two big masses m and m to it on the ends, okay? One of these masses has a charge q, the other mass has no charge at all. And they said that this rod is free to spin in the xy plane, okay? Which means it's spinning around the z-axis. So if I'm going to be computing torques at all, they will be computed in this direction, so they will have values in the z direction, okay? Now, so far, that's basically, and they are saying these m's are small, so that you can treat them as point particles, basically. And then the other thing also is they gave us the electric field pointing in the negative direction above the plane, basically when y is positive, and it's 0 when y is negative. And they said that take this basically direction, the x direction, as some sort of an origin for the angles, and theta when it was 0 when it was along with the x-axis, and when it moves slightly, make theta whatever value it is that moved with it. So basically that's a representation of it. And they tell us to write the vector r that points to the charge q in terms of its coordinates, okay? Now we know R has a magnitude of A because this rod is supposed to be rigid. It's not supposed to be compressing or elongating. So the length of this distance is the same because this is A and this is A. Both of it is, I mean, the whole rod is to A. But its direction is changing. That's the only thing. So if I use Pythagorean theorem in here, the vector R has a projection in the x direction and the y direction. The projection in the x direction is clearly R, which is A in length, times cosine of theta. And the y direction is just A times sine of theta. And it has no z component because the whole rod is just in the xy plane. So the vector R looks like its x component, which is A cosine of theta in the I hat direction, and its y component is A sine of theta in the j hat direction and has no component in the k hat direction. Does this make sense to you?
Yes, it does.
Okay, how about everybody else? Is it so far so good with me?
Yeah, so far it makes sense.
Okay, R has a fixed length. It does not change because the mass is attached to it. The only thing that changes is its direction, theta, potentially. And because of this force, it will change, okay? Now, what else do they ask in here? So write an expression for the vector R. We already wrote it. This is the expression for the electric field, for the position R. I mean, if you want to write it symbolically, I mean, in vector notation, this is A cosine theta, sine theta, 0. A vector whose x component is cosine theta, and sine theta is its y component, and 0 component in the z direction, and its magnitude is A, because it's fixed, it doesn't change. Yes, this is the vector F, the vector of the force F. The vector of the force F is just Q times E, and since E is given to be minus E I hat, or minus E100, and then you just multiply that by Q. Are you guys, everybody's comfortable with this notation of the vectors?
Yes.
Yeah.
Makes more sense like that.
So that's basically how I'm writing these vectors so far. And now the next question, B, determine the torque tau about the center of the rod when theta is some value between 0 and pi. Somewhere in here, 0 and pi. So the electric field is not 0, the force is not 0, so we have definitely a torque, and the torque, I have two ways of finding it, okay? The close your eyes finding method and the actual geometry method. So let's use basically this expression or this one. Whichever way we want it, we'll find the torque. So let's do that. The torque tau with the first method is equal to R cross F, which means that it's the determinant I hat, J hat, K hat, and the components of R are A cosine theta, A sine theta. Oh man, why does it do that? Sin theta, I have to be slow in here, and 0. And the components of the force F are minus QE 0, 0. Are you guys familiar with this way of writing the cross product? Did you do it in your class?
Yes.
Yes. I think we did.
Okay. How about you, Caesar?
Yeah, this is the way I learned how to do it too.
Okay, so it's easy then. Okay, to find the S component, I have to find this determinant. I have to multiply A sine theta by 0 and then multiply 0 by 0. So the I component is equal to 0 minus 0. Plus, or actually minus, I should be careful in here. If I want to find, because it's plus, minus, plus, and so on and so forth, okay? Minus J hat, the same thing. I have 0 times A cosine theta, which is 0. 0 times this number, which is 0. 0 minus 0. Plus now K hat, and for that, I have to multiply 0 by this number, which is 0, minus minus, so it's going to be a positive, Q E A sine theta. I have difficulty writing the sine today, okay? So everything is 0 except the k hat component has a value, and it's positive, okay? Actually, the torque now, if everything is written correctly, the torque tau is going to be Q AE sine theta in the k hat direction. And it's a positive torque. It's very important to see that it's a positive torque. That means it's counterclockwise. Does this make sense to you? The force is pointing this way. Is it its torque counterclockwise or is it clockwise? Which way it's trying to spin it? Counterclockwise or clockwise?
Counterclockwise.
So it makes sense, perfect sense. So we have no problem whatsoever.
Mm-hmm.
So let's try to find that same torque using a different approach, the geometrical method. So the geometrical method basically finds RF. R is A. The length of this vector R is A. So we're going to find it A times the force. The magnitude of the force is just QE. Remember, QE is magnitude. So the magnitude of the first is A. The magnitude of the second is QE. Okay. And it's a positive torque from the geometry. You can clearly see is a positive torque. Time is the sine of the angle between them. Sine of this guy. And what is this guy in terms of theta? This is the vector R. This is the force F. What is this angle in terms of theta? This angle. So look at it this way. You have a line going this way. You have another line, the x-axis, and you have a line joining them. This is theta. So how much is this one?
The exact same.
Is it theta?
Yeah, that's theta too. Because you have two parallels and this are the two inside cutting. There is a theorem that you guys know from way back. Sine theta. So that is the magnitude of the torque, and it's given by the right-hand rule. So it's given by the right-hand rule, meaning this is the, okay, this is where, let's tilt it a little bit to push it in the direction of R hat. I mean R. The R is pointing this way. The force is this way. So the way your palm basically curl, your thumb will point to the force, so it's coming out. I mean the torque, it's coming out. Okay, it's exactly the same thing. And who's coming out is k hat actually. So this is k hat, and that in agreement with this expression. This is close your eyes and do it. You'll find the correct answer. And it's a positive torque, indicating it's a clockwise torque. And this is actually with using the geometry and all of that and using this relationship, and you're going to find the same answer. Does this make sense to you guys both ways for the torque?
Yes.
Yeah.
Okay, you need to be comfortable with torque because we are dealing with dipoles and we're going to be calculating torques a lot, okay, in this class. So that's a concept. I know that probably Caesar is the one who asked this question, but I'm just making sure that you guys need to be comfortable with calculating torques, okay? Either way. So that's question B, I think, we're in this problem, question B. Question C, determine the torque on the rod when on the rod about its center when theta is greater than pi and less than 2 pi. You guys know the answer to that. How much torque when this whole theta now becomes more than 180 degrees? How much the force is in that region? When this rod spins so that it's greater than 180 degrees, but less than 360 degrees, when it's in this side. So this theta now, think about it, has moved all the way somewhere in here. So there is a charge Q in here, but how much force do I have now?
0?
On this side. Yeah, so how much torque do you think we will have in here?
0.
Going to be 0 because the force is 0, there is no torque. The other side, when this mass, when it moves to the other side, it doesn't matter because it has no charge. Although it's sitting in an electric field, then it has no force. The reason why we don't bother with this mass is because it has no charge. And so whether or not it's sitting in here or sitting there, it doesn't matter for it, because remember, the force, the electrostatic force is equal to the charge times the electric field. although this mass, the second mass, when it moves here, it's inside the second electric field, but it has no charge, so there is no force. And this charge in here, when it moves all the way here, now it becomes in the third quadrant or the fourth quadrant. It doesn't matter at that point because there is no electric field there. So although you have a charge, but you don't have an electric field. So the answer to this question is straightforward. Tau is equal to 0. Question, what is it? Question C. Question C, determine the torque on the rod when theta. So that's tau is equal to 0 in the third and fourth quadrants, because F is equal to 0 there, because E is equal to 0. Does this make sense?
Yes.
Yes.
Okay. And D, what is the moment of inertia of the system about the z-axis? The moment of inertia, basically you have 2-point charges of mass m situated at a distance a from the center of rotation. So we want to find the moment of inertia for this mass. It's a point charge. The rod itself is negligible mass, so we don't worry about it. So the torque for the moment of inertia of this point particle is just the mass times the distance squared. And this one is also the mass times the distance squared. So the moment of inertia is just the sum of the two moments of inertia, and it should be I is just twice the big M times a squared, because M is a point particle. And the rod of negligible mass. Meaning it has no moment of inertia. Is this easy enough so far for the moment of inertia? You guys saw this stuff in here. This is the easiest moment of inertia that you probably could do in this case. From physics 4a, that is. This point particle. You remember that?
A little bit.
Yeah, the moment of inertia in general is defined by, it starts with a point particle, and it's the equivalent of the mass, equivalent to the inertia, except that this is for rotation. And for a point charge, for a point particle is actually equal to the mass times the distance squared from where you're calculating it. And they tell you specifically to calculate it with respect to the z-axis. And the z-axis is passing by the origin. So with respect to the z-axis, the moment of inertia of this point particle is its mass times the distance squared. And the distance is, in this case, is just a. It's not a vector, it's a scalar, remember. The whole thing is a scalar. And the same thing is true for this one. Does this ring a bell for everybody now?
Yes, it does.
Yeah.
Yeah, you have two of them though. It's the only thing. Even though the other one doesn't have a charge, it still have inertia in it. And that is how it expresses itself, by contributing to the moment of inertia. Correct?
Mm-hmm.
Okay, so let's continue now. The potential energy use of theta is determined by tau equals to minus, because this torque derives off a potential. And again, that argument probably you have done it in physics 4a, where in this case tau is equal to the gradient with a minus sign to come up with the conservative forces, with the conservation of the energy, and you use this symbol for it. This is similar to when you did F equals to minus the derivative of U with respect to position for the spring, for example, because the spring is equal to minus what? Minus kx. And so when you write this one as being minus du over dx, you integrate and you will find that U is equal to 1/2 of kx squared for the spring. And you do the same thing for the force of gravity, which is pointing down, and the displacement is upward. It's equal to minus mg. And this is equal to minus the potential energy with respect to the height, in this case, y. And you integrate this expression again, you get rid of the minus, and then the potential energy, gravitational potential energy, is equal to mgy, because it's a constant. Mg is constant, so it's mgy. So that's basically the potential energy, but there is actually a table that you guys probably have worked on, and that is the linear motion versus the rotational motion. rotational dynamics, that is. And then you started to build up a dictionary. For example, the displacement in 1D, actually, this has to be 1D. You use X, and here you use theta, and the velocity you use V, and in here you use omega. The acceleration you use A. The angular acceleration is alpha, which is the second derivative. This is the first derivative of theta. This is the second derivative of theta, or the first derivative of omega. And this is actually the first derivative of X, and this is the second derivative of X, or the first derivative of the velocity. And then you also come up with the mass used in here. I is used in here. The force is in here. The torque is in here. And F equals to ma on one side is equivalent to I alpha on the other. You guys remember this discussion that you guys had?
Yeah.
F equals to ma.
It looks familiar.
Tau equals to I alpha. So this is a dictionary. Actually, this is an SAT question that used to come in the exams, basically to find this dictionary correspondence between one and the other, one and the other, one and the other. So basically, one of the expressions that we use in here is for force that derives off of potential is minus du over dx. So you use your dictionary. What is the equivalent of F? It's tau. Okay, the energy is the energy. It doesn't change. So what is the equivalent of X is theta. So that's basically the point being in here in this question. So they said use this fact in here, that the fact that the torque is equal to minus du over d theta to find basically to find the potential now. Use this equation to write an expression for use of theta between 0 and 4 pi, okay? Using the convention that use of 0 is equal to 0. So we're going to take the origin, because all of this integrations require an origin for the integration. Actually, because I'm integrating, usually I have a constant in here. So the potential energy is defined with respect with the constant. And here we take the spring when it's completely stretched as zero potential energy. That's how we fix the constant. In this case, we take a level, it doesn't matter which, to be the origin of the potential energy for the gravitational potential energy to be that. So there is an indetermination when it comes to the potential energy because of this integration, because of the constants. So you have to choose the origin of the potential energy. And this problem, they tell you, take use of 0, the potential. Basically, we're trying to find use of theta. That's the key. Take when theta was equal to 0, the potential energy was 0. In other words, when the rod is sitting still, on this side, take it to be 0 potential. That's the origin of the potential energy. So the system either builds up potential energy or basically goes in the opposite direction of the potential energy, depending, okay? So if you take this level, for example, the height to be the potential energy for the gravitational potential energy, you take an object, it's going to have a positive potential energy, so it's going to fall and convert it. If you put it in here, it's not going to fall upward at all. So that's basically the same technique in here, okay? So they say, because at some point you're going to integrate. So you need to pull up a constant and you need to deal with that constant. So this is what they tell you to do to find that integration. Does this make sense? Yes?
Yeah.
Because we just found tau. This is tau. And we're going to write tau as equal to minus that derivative. So we're going to write tau now. Here's the thing. We found tau to be AQE sine theta in magnitude. That's the torque tau. AQE sine theta. And this, we're going to require it to be minus du over d theta. If we integrate this expression with respect to theta, we're going to find a constant. How do we handle the constant? By just ensuring that use of 0 is equal to 0. Okay? So let's do this integration first and see what we're dealing with, and then we'll deal with the constants and all of that, okay? So if I integrate this expression is the same thing as du is equal to minus QEA sine theta d theta. And the integral of minus sine theta is, what is the antiderivative of sine theta? Or what is the antiderivative of cosine theta? Which function, if I take its derivative, I find, so this is use of theta. Which function, if I take its derivative, I find minus sine theta?
Isn't it cosine?
Do you guys agree with
Yeah, I think right. Yeah, it's cosine.
Yeah, I
The
agree with cosine.
the derivative of the cosine? It's minus sine. So it's QEA cosine of theta plus something. Plus,
D over D theta over D.
no, plus, when you integrate, we already integrated. I didn't, we already did
Isn't
that.
it plus
So
C?
plus the speed of light. Is that what you're saying, Drake?
I mean, plus a constant.
Okay. That's
Yeah, not
true.
the speed of light.
Constant, okay? So plus a constant. Does everybody agree?
Yeah.
Yes.
Okay, so that's basically, we just integrated this expression. Now we have to deal with that constant, okay? They say to take theta equals to 0, but you have to be careful now. We're going to integrate this from 0 to 4 pi. And make sure that use of theta is continuous. So we're going to do it from 0 to 4 pi. First of all, this value that I wrote in here is not correct. It's only correct between 0 and pi, because that's the torque. The torque was equal to this value only in that region. It's 0 on the other side. Okay? So from 0 to pi, this is true. Yes? Because from pi to 2 pi, I have 0 on the other side. I have to integrate 0, which is going to be a constant. Correcto?
Right.
So in this case, the constant, I knew that use of 0 is equal to 0. That means that QEA cosine of 0 is just 1, plus the constant is equal to 0. That means the constant is actually equal to minus QEA. That's it. And then in general, then, in this region only, use of theta will simply be equal to this number minus the same number. So it's going to be just QEA times cosine of theta minus 1. Only here, in this region only. Yes?
Yes.
So I need to go to the next region now. Now from pi to 2 pi. From pi to 2 pi. Tau is equal to 0, which is equal to minus du over dt. Du over dt, I'm sorry, du over d theta. Okay? What is the integral of 0? U in this region is equal to which function if I take its derivative I find 0? Come on, guys. Which function I can take its derivative, it gives me 0?
Is it a constant?
Yeah, it's a constant. Yeah, because if I take the derivative of u now, this is use of theta, by the way. It's constant, because if it's take its derivative, it's going to give me 0, correct?
Right.
So the potential energy from 0 to 2 pi is going to be constant. And how much is this constant? We know it has to be continuous. That's what they said. And in here, use of pi was a value. So in here, I have a value for use of pi from the previous. Use of pi is equal to QEA times minus 1, because cosine of pi is minus 1, minus 1. So this is equal to minus 2QEA. Correct?
Right.
Yeah.
So this must be that value too. This is constant throughout. Minus QEA, two of them. Because this function better be continuous. So throughout this entire space now, from pi to 2 pi, here, the potential is just a fixed number. It doesn't change. So you're at the same level. You went to the second floor. And now you are in the hotel moving from room to room on the second floor because the potential is not changing. You're on the same level. Yes?
Yes.
Yeah.
So it makes sense because you reach that point, you use the continuity condition. This is the continuity they require that this function better be continuous. We're not done. We have to go all the way to 4 pi. We just reached 2 pi. So now we're going to go from 2 pi to 3 pi. 2 pi to 3 pi. Again, torque is defined by that expression again. We're back to this one because in that region, the electric field now, so if this charge now spins and becomes all the way here, now again, the torque is not zero. I mean, the torque is not zero. Yes, it's equal to this very same expression, QAE sine theta. So now again, this step is going to be repeated one more time. QAE sine theta is equal to minus du over d theta. And again, if I integrate this expression, just a repetition of the previous one, it's going to give me u sub theta is going to be equal to QAE cosine theta plus another constant. This new constant better make this one continuous. By the time we reach that theta equals to 2 pi, this value is equal to this number. So when theta is equal to 2 pi now, in that point, remember, it was a value 0 to begin with here. That's how we started this. And we went all the way here to a negative value. And then it was constant all the way throughout now. Now it's still that constant by the time we reach 2 pi. And that constant is exactly equal to negative 2QEA. So that is that potential then, u sub 2 pi is equal to, from the previous one, in order for it to be continuous so that it doesn't jump into another value, must be equal to QAE cosine of 2 pi plus constant. Constant. Oh man, C-O. Can I write C-O-N-S-T? Okay. What is cosine of 2 pi? Isn't that 1?
Yes.
So when we move this to the other side, I will have 3 of them. So the new constant that makes sure that the continuity is fixed is going to be minus 3 QEA. And then the expression now looks a lot different. So now u sub theta in this region is going to be QAE times cosine of theta plus the constant, because the constant has these terms also, I took them out, but I have a 3 in here. We just reached 3 pi. Now we need to move all the way to 4 pi. So now we reached from, what is the shape? From 2 pi to 3 pi, that is the function, how it looks like. This function of the potential energy is continuous. It started from 0 and then smoothly transited to pi. At that point, stayed constant. So initially it was changing as a cosine function. And then now it stayed constant throughout the second and the third, the third and the fourth quadrant. And then it started changing again between the first and the second quadrant. And now it's going to become again from 3 pi to 4 pi. It's going to become again a constant because the torque is 0 in that region too. So if I integrate the 0, u sub tau is going to be a new constant. And this new constant is ensured by the continuity of this function at tau equals to 3 pi. So at tau equals to 3 pi, this function gives me that constant. U sub 3 pi is equal to QAE times cosine of 3 pi minus 3. And what is cosine of 3 pi? Cosine of, what is it, 360 plus 180? It doesn't matter, it's going to be a negative 1. You guys see that this is a negative 1?
Yes.
So negative 1 minus 3, that's a negative 4. So now it's going to be negative 4 QAE. This process actually is not going to stop there. Actually, the whole thing is going to move from plane to plane to plane. And this is actually the conformal mapping that is known, where you have function that is actually, I mean, it looks like it's periodic, but it's not. It's actually the potential itself, because it's an integral, does this behavior. Okay, but they asked us to stop at 4 pi. I mean, if they tell us to continue all the way to 73 pi, then we are going to continue this game. You get the exercise, guys?
Yes.
Mm-hmm.
So use the convention that make sure that u sub theta is continuous. The angular velocity of the rod is omega sub theta using tau equals to 1/2 I second derivative of tau with respect to time. Show that I 1/2 of I omega squared plus u tau is conserved quantity. Okay, using energy conservation, determine the expression for the angular velocity of the nth time the position of the positive charge crosses the negative y-axis. Oh man, okay. Because actually we use this trick to find the torque, to find the energy, so it must be conservative, okay? So let's see here now. 1/2 of I omega squared, which is really the kinetic energy of rotation, okay? 1/2 of I times, what did they say? The second derivative of, no, the derivative of theta with respect to tau, t, and that is basically the kinetic energy of rotation. But let's see here what the question is saying. The angular velocity omega sub tau using this expression, show that 1/2 of I omega. Okay, here is the deal. You have I, the second derivative of tau with respect to t is equal to tau. And tau, if you guys remember, is equal to minus du over d theta, correct? What I'm going to do now is basically rearrange this expression a little bit, and we're in business. In other words, I'm going to multiply this expression by d theta over dt, and this expression by d theta over dt, okay? So let me make sure I know what I'm saying in here. And integrate the expression, and integrate the expression. And yes, I think so. So if I move this to the other side, the minus becomes a positive. So what I have in here is I times d second of theta with respect to t times d sub theta with respect to t plus du over dt is equal to 0. Because I basically canceled, which is really an illegal operation. It's not the correct way of saying it. You have to use a finite values, delta u and delta theta and delta t, and then cancel, and after that take the limit when deltas go to 0, and then you redefine the derivative that way, but it's going to amount to the same thing. So practically you're going to get this value. Is this expression correct from here, yes or no? Yes or no? What I did was actually I just rearranged the term. I multiplied this because remember we say tau is equal to I alpha, and I alpha is the second derivative of theta with respect to t. So this is the equivalent of Newton's second law of motion for the case of this rotational motion, correct?
Right.
Right.
So all I did is multiply this expression by the angular velocity d theta over dt on both sides.
Okay.
So far so good?
Yeah.
Yes.
And then I used the fact that tau itself is actually equal to minus du over d theta. That's how we got all of this business in here, trying to find things. Yes?
Yeah.
So now simplify, quote unquote simplify. You have to be very careful with this word, okay? I'm really being loose in here and using the word simplify because technically, mathematically, this is not correct, okay? But you can argue because the simplification can only happen for finite values. This is not a finite value. So what you do in this case, you go into a delta t amount of time and measure delta U and measure delta T and measure delta theta and simplify before taking the limit. It's going to amount to the same thing. So the simplification would work in here. You guys understand? So d theta and d theta cancel, and I'm left with minus du over dt. Move it to the other side, it's going to be a positive du over dt. Yes? Am I losing some
Right.
people so far? Okay. Now integrate this expression side by side. The integral of 0 is going to be constant on the other side. The integral of this expression, first of all, this side, because the integral is a actually linear operation. So in here, I'm going to find u, the potential energy, plus the integral with respect to time, by the way. That's how I get rid of this dt. So it's going to be I times d squared of theta with respect to dt squared times d theta over dt dt. Okay? Yes? This expression actually can be written a little bit easier if I write it as the derivative of the angular velocity with respect to t times the angular velocity, because this is omega times dt. Yes? Because the derivative, the alpha is actually, I wrote it upstairs, alpha is actually equal to, the angular velocity is equal to the derivative of omega, omega dot. So the second derivative of alpha with respect to time is just d omega over dt. Yes? Does this make sense? So I just rewrote these terms.
Right.
Okay. Again, I'm going to make a simplification, which is kind of nonsense. We have to take the delta t first and the delta omega, take the simplification, and then take the limit when the deltas go to infinitesimal quantities, meaning the d's, then you're going to be fine at that point. So assuming that that's correct, so I'm left with integrating omega d omega. And what is the integral of omega d omega?
So one
What
half.
is the integral of x dx?
Is it 1/2 omega squared?
1/2 of omega squared, that's correct. So this term, if I integrate it now, the first term is going to give me 1/2 of I omega squared plus u is equal to constant. And that's exactly what we needed. This is the kinetic energy. This is the potential energy. Kinetic energy plus potential energy is equal to a constant. That's what they want you to show in this question, that this energy is conserved. The total energy is conserved. Mechanical energy is conserved in this process. Yes?
Yeah.
Okay. So show that the total 1/2 of I omega squared plus u sub theta is conserved, and that it is conserved because it's always equal to a constant when you add these two quantities. Okay. Using energy conservation, determine an expression for the angular velocity at the nth time the positive charge crosses the negative y-axis. Okay. The negative y-axis. This values, if you notice in here, the first time around, what is the time? The first time around, the potential energy was equal to between first of all pi and 2 pi was equal to minus 2 QEA. The second time when it crossed it, minus 4 EQA. So every time we cross the y-axis in the negative direction, the nth time, the first time it was minus 2 QEA. The second time it was minus 4 QA. If we do this, the next time around, it's going to be minus 6 QEA. So every time I multiply n, the third time I multiply n by 2, so that's basically what this thing is saying. So that means that the first time around, 1/2, or the nth time around, is going to be 1/2 of omega n squared minus 2nQAE is equal to a constant. Okay, solve this expression for omega n. okay? And that's the end of it, okay? That's the last question. Is it the last question in here? Let me look at this thing in here. If it's even asked. And this constant is what? That's the key question in here. Is this constant 0? It seems like what they are doing in here, and I'm not sure, honestly. I'm looking at the solution in here, okay? Not the solution, they give you the answer only. I don't know if you guys saw it. They take this constant to be 0, and probably the rationale behind it is because initially it did not have that energy when we started with. So initially it was 0 on this side. So when it comes back on the other side, it must have that continuity again condition. So it's going to be 0 all the time. So this sum of the energies is always 0. So if I equate that to 0, then I'm going to solve for 1/2 times I, and I, as you guys remember, is 2m times a squared times omega squared minus 2n QAE is equal to 0. And if I solve, this is omega n. If I solve for this omega in here, first of all, this 2 cancels that 2, and this a cancels that a, and omega n will be simply equal to 2n times QE divided by ma under the square root, because this is square value. So that is the answer to the question. Okay. Up to this point, honestly, I think the rationale behind it is the fact that when we started with this problem, we started basically with 0 potential energy, which is really by continuity. It must be also true for the 4th quadrant, and the 4th quadrant is similar to the 3rd quadrant. So the potential, the total energy, the total mechanical energy is always 0. So there's this flip-flop between the kinetic and potential all the time in such a way that sum stays 0 as we started with. So the total mechanical energy is 0. So that is how you get this value, because this constant has to be determined somehow. And you determine by the initial conditions, and the initial conditions state that the problem had no energy to start with. So once you move it, the electric field starts to move it by changing the potential energy on the expense of the kinetic energy and vice versa. Every time it crosses the y-axis, it's going to have this value. It's going to be this true value for the angular velocity with which it's going to spin. So basically, it's gaining speed, losing potential energy. Once it reaches the pi version, it's going to continue spinning basically at that point, because there is no torque in that region. And then it's going to continue and changing and changing. And n now seems to be accelerating this particle, because the next time around it's going to gain more potential and more potential. So there is a kick. Every time it goes back to the positive region, the electric field would pose a positive charge. And then it's going to go constant. And then it kicks it. And then it's going to go constant. And then it kicks it and give it more acceleration, angular acceleration. And then, you guys understand the process? Each time it passes through, it's going to gain more and more speed. Does this make sense?
Yeah, it's making sense.
Okay, because you have one side that is positive and the other side has nothing in it. So during this cycle where this is positive, it's going to accelerate it until at some point there is no acceleration. So throughout this entire cycle, this has no mass, has no charge. So it's has no charge, so it's not going to do anything. So this is basically how the cycle is looking now. So the first time around, it has 0 energy we started with. The minute we gave it an angle, even though a small one, the electric field now give it a torque, and the electric field will move it all the way here the first time around, accelerating it, increasing its velocity on the expense of the potential energy, because the potential energy went from 0 to a negative 2QU, so it went down, okay? So now the potential energy went down, the kinetic energy went up, but during this entire cycle, there is no torque. So it's going to continue with a constant angular velocity. The minute it reaches this point, it's going to gain kinetic energy now, and its potential energy drops from minus 2QU. Remember, it started from 0. And now it has minus 2q, this entire first section, first passage, if you wish, first time it passes through. It's going to drop its potential energy to minus 4, or whatever that is, the new value. In doing so, it's going to gain angular velocity. During this entire cycle, the second time around, it's going to have this value 2 now. And it's going to go around constant. And then, because there is no electric field in here, there is no force in here, and there is no torque in here. So it's going to be constant, cruising at constant speed. And then it's going to gain in here because there is actually an E, and there is actually an F, and there is actually a tau during this first and second quadrant. So every time it passes through the y-axis next time around, it's going to have more energy in it, more energy. So this looks like it's an accelerator. Accelerator, it doesn't have to be nuclear. Accelerator. Okay. Does this make sense?
Yes.
Yeah, the explanation of it definitely makes sense. When I saw the 0, I was initially thinking it's because all the energy is conserved, so there's no loss of energy, if that makes sense. Since
yeah, go ahead.
Since when the energy, well, not when the energy, but when the electric field makes that one charge side go through and then it passes through where it has no charge, like you had said, it's basically spending all of its I don't know what the correct term is for it again, but it's energy that it's gained from going through that electric field. It spends it where it has none of that. And then as it goes through again, it passes towards the electric field and it goes on with the cycle. So initially there's no loss of energy. That's how I interpreted it when you said the answer would be 0, which now when you explain it, yeah, it definitely goes more into the specifics as to why it's now 0.
This is the setup. They started with 0 when the thing was laying down this way. They said, take it to be 0, okay?
Mm-hmm.
And they said, actually, if you read the problem again, they said to give it slight angle theta. The minute you give it that slight tilt in here, this thing is not going to stop because there is a torque now that is not 0, okay? Because tau, remember, it has a sine theta in it. What is tau to begin with? The one that we calculated. It has a sine theta in it. Yes, when theta is 0, it's going to be fine. It's going to be stable. It's metastable. It's not completely stable. The minute you give it a kick, it wants to go all the way to the other side so that the charge will line itself to the other side. Do you understand? But then at that point, it has inertia, so it's going to continue cruising with the same speed throughout the entire cycle. The minute it comes back again, so it's going to pick up now speed. So it's acting like a motor also, okay? So the minute it comes back again during that entire cycle, it's gaining now speed because again, it's not a stable configuration. It wants to go in such a way to be stable on the other side, okay? Because sine theta, yes, is 0. But sine theta is actually equal to negative 0 also on the other side when theta is 180 degrees. So the torque also is 0 when it's completely lined up. So the system is in equilibrium whether theta is 0 or whether theta is equal to 180 degrees, but it wants to be in 180 degrees because that's where the electric field and the force are actually, the electric field and the torque are actually in parallel. That is actually the state of minimum energy, but the thing is, it's not going to stop there. It's going to continue cruising with that constant angular velocity until it comes to an unstable situation. And the minute, even with a breeze, even if somebody sneezes next to it, it's going to jump to the next state and continue. It doesn't need that. The inertia would continue that. The first time around, you need somebody to sneeze next to it for it to move. But if you leave it at theta equal to 0, it's going to stay at theta equal to 0. So it started with no energy because u sub 0 is 0 and it started from rest. So initially it has what not moving. So omega was 0 and also u was 0. The potential energy was 0. That's why this constant better be 0 because we started with 0. So it needs to stay 0 everywhere. It should not change to any value because initially, when you think more about the problem, you understand it better. Initially, it started from rest. They said that just give it a slight nudge. I think they use the word nudge, okay? From theta equals to 0. That means that it started from 0. Omega is 0. And also theta was 0. That means the potential, we took it to be 0 by definition there. That was our starting potential there. So from that point on, the initial total energy was 0. So it better stay 0 according to this math argument in here that I made. I went through to argue that this whole thing is constant, and it's equal to whatever constant you start with or any constant in the process. So initially it was 0, it's going to stay 0 forever and ever and ever. So this gives me a condition on omega n as a function of n every time we pass through the y-axis. As a matter of fact, every time we are in the, because that entire region has a torque that is 0, so the angular velocity is constant throughout that region, whether we are in the 3rd quadrant or 4th quadrant. Everybody good with this problem?
Yes.
Okay, I'm gonna adjust the
Yeah.
grades on this problem because I think it's a mess. I mean, honestly, I did not really think that it's gonna be this hard. Okay. How about the other problems now? Let me look at the other problems quickly. Man, we spent, I mean, an hour on this problem. But if again, I usually when I'm solving, especially on class, I go through in verbose, I go too much detail. Sometimes they become a little bit overwhelming. Please let me know if they become too much, okay?
Professor, I have a question.
Yes.
So, I've been doing a few examples in the actual physics book just to like get a little more practice and, you know, get a little more experience. And I keep encountering the same issue. So in the book, it says that the equation for the electric field is 1 over 4 pi epsilon times the Q over R squared. And then it states that the E is equal to 9 times 10 to the negative, I think it's 12. And then K is equal to 9 times 10 to the 9. So when I plug it in, the book had said to plug in both numbers, but it doesn't make sense because when I do, the numbers I get aren't the same. So what I've been doing instead is I plug in the K value. So the 9.0 times 10 to the 9. And when I multiply by Q1, I do the value of Q times 10 to the negative 9.
Mhm.
But I don't understand why. Because that
Okay, hold on.
it gives me the right number, but I don't know why it is.
Okay, first of all, when you're doing mastering, and this is a big warning, and I'm going to send a message, please, if you don't see it by tomorrow, send me a reminder because I really need to send it to everybody. In mastering, you use the symbol K. Don't use 1 over 4 pi epsilon naught.
Okay.
When you're doing the homework. It's the same thing, okay? But they use this notation extensively. So if you use 1 over 4 pi epsilon naught, the grading might give you wrong, okay? So use K. Are we good on that?
Yeah, that's why I learned to use K because I kept putting 1 over 4 pi epsilon naught and it kept saying it was wrong and I didn't know why. So then I put K instead, but by the time I put K, I ran out of tries.
Okay, so I'm gonna send a message to everybody, hopefully by no later than tomorrow. And I know mastering had all of this bugs in it, so that's something that is kind of an issue. But hopefully the physics you learn from it is more than this bugs in it. So this is the first thing. So use K not 1 over 4 pi epsilon naught. The value of K, sometimes it's picky about it. It's 8.99 times 10 to the power 9. That is the value in SI. And SI, because remember, K times Q1, Q2, that's 2 charges divided by meter squared, is Newton. So units for K are Newton meter squared over Coulomb squared. So this is a Newton meter squared per Coulomb squared. So that's the units for it, okay? So that's one thing. In class and in exams, you're fine to use 9 times 10 to the power 9, okay? That is fine. Coulomb squared, okay? Now, if you calculate epsilon naught using the first expression, okay, it's going to be 1 over 4 pi epsilon naught is equal to 8.99 times 10 to the power 9. I'm not going to write the units, they're there. So from here, I'm going to find the value of epsilon naught to be simply 1 over 4 pi times 8.99 times 10 to the power 9. In other words, epsilon naught will be something 10 to the power negative 12. Okay, that's the permittivity of the vacuum. What is my calculator here?
Yeah, it's 8.99 times 10 to the negative 12.
It's 8? No, it should be 8.5 or something, not 8.9, is it?
The book said 8.9.
Okay, let me check, okay? Just to make sure, okay, 4 pi 8.99, 10 to the power negative 10 to the power 9 in this situation. And the whole thing is 8.85. That is actually correct. It should be 8.85.
Yeah.
Times 10 to the negative 12. And the units for this guy are basically the opposites of this unit, okay? The opposites of this unit, because 4 pi is just a number. So it's going to be Coulomb squared per Newton meter squared, okay? So this is the
That makes so
permittivity.
much sense. I thought we were plugging in both values. So I thought that when we did, okay, so like 1 over 4 pi epsilon naught, that was one value. And so we were doing multiplying it across, but on the denominator, it was the 8.85 times 10 to the negative 12. And on the numerator, it was 9 times 10 to the 9.
Okay. It's only one or the other two, okay? The way I memorize it, okay? I don't care about the other 4 pi and all of that. I know only 1 over 4 pi epsilon naught is 9 times 10 to the power 9. If I am picky about it, somebody is asking me, what is the exact number? I'm gonna look for it and it's 8.99 actually. It's actually, there is more digits in it, but 8.99 for most practical purposes is correct. I never honestly memorize the value of epsilon naught. If I really need it, a problem, I pull it from this expression. 1 over 4 pi epsilon naught equals to 9 times to the power 9, and I put it from there, okay? But please remind me, and this is your job, Marcella, now, by tomorrow, if you don't see a message concerning this issue, please remind me that saying that, hey, you're supposed to send a message to everybody stating that use kappa or k for instead of 1 over 4 pi epsilon naught, because this book uses k everywhere, okay? And I avoid that because some other reasons, okay? You will see them down the road, actually. Okay.
Okay, thank you.
Okay. There is another similar to it situation that we're going to see down the road. It's mu naught over 4 pi. I think the book uses different notation for it, but you will see me using mu naught over 4 pi. That's for magnetic fields. For electric fields, 1 over 4 pi epsilon naught, but we're just going a step ahead of ourselves in here for this one. Okay. Yes?
Yes.
Okay, mastering is crashed on me, so I probably have to, yes, continue. Oh man, I have to sign back in.
It does that.
Yeah, now I have to. Okay, let me sign in again. If we don't use it after probably 5 minutes, it's gonna say a timeout on you, or I don't know how long. Okay, let me go back into it now. Are you still guys looking at the shared screen, or what are you looking at?
We're looking at the OneNote.
Okay, good. Because I want to see what other problems are in there, because I think I looked at the other problems. They look decent enough. This is a 94 is a.
I think the only really long one was 94.
Yeah, 94 is not really a friendly problem. So I'm going to regrade this problem, okay? Because I see it says issues. And even problem 70 seems to be giving people headaches, and problem 89, but not as much, okay? Let me look at problem. Oops, I moved the wrong slide, man. Are you still looking at the OneNote? Because I tried to move something and I moved it.
Yeah, it's
Yes.
It's still OneNote, yeah.
Okay, so problem 61 is similar to what we did in class. Similar to it, not exactly. Actually, this one is a little bit simpler because with this problem, you have two masses, M1 and M2. I mean, Q1 and Q1 on one side and Q2 on the other side. The masses are the same. And basically, there is a string suspending these two charges. And the charges are, well, let me read. Two small spheres of mass 14.3 grams are hung by silk threads of length 1.3 meters. So we're given this length L. from a common point when the spheres are given equal charges, so that Q1 is equal to Q2 is equal to Q. So Q1 and Q2 are equal to one another. Each thread is making a 22-degree angle with the vertical. So this angle is 22 degrees, okay? Not the whole thing, just this angle is 22 degrees from the vertical. So the first question is basically, what is it? Okay, I'm not gonna do this problem because I assume that you guys should not have a problem with it. You have mg on one side because they gave you m. You have the tension on the other side, T, okay? And you have a repulsive force in here, and the reason why it's repulsive is because the two charges are the same, okay? So this force is pointing this way. And now this angle, because you will need angles abound, okay? This angle is 22 degrees, and you will have mg equals to T times cosine of 22 degrees. And also T times sine of 22 degrees is equal to this force, which is just 1 over 4 pi. And I just used 4 pi again, times Q squared, because the two charges are the same, divided by the distance, this distance squared. So you need to find this distance. Again, they give you L. You can find this one using sine of theta, sine of L, sine of 22 degrees times L. That gives you this one multiplied by 2. Don't forget the 2. Otherwise, you're going to get something wrong. And now you have all this one. And from here, you can determine Q. You can determine everything on this problem. Does this problem make sense? Does this problem make sense to you guys?
I haven't tried it yet. I was focusing on the other ones.
Yeah, this one was more similar to the one like what we're learning right now. It wasn't that bad.
Yeah, like the one we did in class. So basically mg, m, and t. I mean, not mg. What is this one? This is the electrostatic force. So this is 1 over 4 pi epsilon naught. The product of the two charges, then they are the same charge. So it's Q squared divided by this distance squared. This distance squared. Okay? And you need this distance, which is just twice this one. And this one is simply equal to sine of 22 degrees times L, because this is also L. And from here, you're in business. You have found D. You know what D is. So you can find Q. You can answer all of the questions about it, okay? The tension is related to mg because they gave you the mass. It's 14.3 grams or something like that. Maybe your numbers are slightly different, but that's another issue in there, okay? 14.3, at least the numbers that I'm looking in here, and the L is given, and the questions are typical question. This is actually an experiment to find the value of so what was the question? First question is draw the free body diagram. Here is the free body diagram for one of the charges. And the second question is draw for the right one. So you draw both of them actually, and then find the charge Q. You're going to equate everything. So the charge Q, this force must be equal to the tension times sine of theta, which is sine of 22 degrees. You don't know what T is, that's fine. Mg is equal to T times cosine of 22 degrees. You take the ratio of those two expressions, all of a sudden you're dealing with a tangent on one side, and get rid of the T, and now you're finding a value because you have M, you have G. You might need to use 9.8, don't use 10, okay? D, and this value is 8.99, use kappa for it if you need to, and that's it. Okay? So that's easy enough. You guys, you should not have difficulty with this one. Do you guys, do you want to do this in detail or you're fine?
I'm pretty good with it.
Okay.
Yep.
So let's move on to the next problem. The next problem is a charge of negative 2.55 nanocoulombs is placed at the origin of an X and Y coordinate, and a charge of positive 1.55 nanocoulomb is placed at a position 3.5 centimeters. Okay, so we have to be careful in here. I have to draw things in here. So on an XY coordinate system, on this problem, you have a charge of a negative 2.55, at least the problem I'm given, 2.559, and at a distance 3.5 centimeters, here is 3.5 centimeters in the y direction, you have a charge that is 1.55 nanocoulomb. So this distance is actually equal to 3.5 centimeters, 3.75 centimeters, okay, on the y-axis. Okay. If a third charge of 5 nanocoulombs, positive 5 nanocoulombs, is now placed at the point x equals to 2.6 centimeters and 3.7, so apparently it's in the same height, at least the problem that I was given, but it's a 2.6 centimeters from this one. So this distance is 2.6 centimeters from the origin, and we have a 5 nanocoulomb in here, okay? If a is now placed in the, find the x and y components of the total force exerted on this charge by the other two charges. I have to use a superposition. So there is a force. This is negative. So there is this force in here. I need to find this distance. Okay. This distance is clearly, using the Pythagorean theorem, is equal to the square root of, so let's call this distance d1. So this distance is equal to d1 basically, is equal to the square root of 2.6 centimeters squared plus 3.75 centimeters squared. And don't forget to multiply by 10 to the negative 2 to convert it back to meters, because this number is going to be in centimeters. Now I have d1. So when I square this, it's going to be just the square root of the square root, which is just whatever you guys end up with. And the force then is going to be pointing this way. So F1 in magnitude only. F1 in magnitude is K times these two charges, 2.55 times 5 times 10 to the negative 18, because nano is 10 to the negative 9. So this is negative 18 coulomb squared, divided by this distance squared, which is 2.6 squared plus 3.75 squared, the whole thing times 10 to the negative 4. Oops, why is this? Times 10 to the negative 4. And this is F1 in magnitude, not in direction. I need to find F2 now. F2, this is positive. This is positive, so F2 is pointing this way now. And F2 in magnitude, the distance between them is 2.6 centimeters. So for F2 is equal to simply K, again, times the product of the two charges, which is 1.55 times 5 times 10 to the negative 18. Again, both of them are in nanocoulombs, divided by the distance squared, which is 2.6 squared times 10 to the negative 4. Okay, so that's the magnitude of these forces. But they want the total force now as a vector, so which is fine. I can use whichever method you like. This force F1, if I can find what this angle is, and it's easy to find, its tangent is actually equal to 3.75 divided by 2.6, then I'm in business, because this force now F1, I can write it as this magnitude F1, which is a numerical value in there that I'm going to come up with, and its y component is going to be given by the, what is it? The x component, I'm sorry, is going to be this magnitude times a cosine, or times the sine of this angle, times the sine of theta. I'm going to call it theta. And theta is actually the arc tangent of 3.75 divided by 2.6. I don't need to convert in here because the centimeter cancels the centimeter. And the y component is the same thing, is equal to cosine, because it's the adjacent to, did I do it wrong? This is the adjacent, this is the cosine, I'm sorry. And this is the sine of this angle, arc tangent of 3.75 divided by 2.6. The only problem with this is the direction. This is negative. And this is negative. Both of them are negative. Okay? So this is F1 plus the other force now, which is completely in the positive x-axis. F2 is completely in the positive x-axis. So I can write it as a vector I hat. And add these two vectors and that's it. Okay? And deal with the algebra in that. Do you guys understand that this is just plug in numbers now?
Yes.
Okay. So what's the next? Find the magnitude of this force. Once you find its two components, you just add the square root of its x component squared plus its y component squared. It's going to be a tiny force though. Okay. Find the direction of this force. Again, the direction of the force, because you're going to find the vector in here. You're going to find, so this is just F now. You're going to find F that has an x component in the I hat direction plus a y component and the j hat direction. So you're gonna, when you do this algebra, when everything is settled in here. So the magnitude is simply going to be the square root of fx squared plus fy squared. And the direction is going to be the direction of this vector f again. So theta, you're going to call it theta. It's just the arc tangent of the y component over the x component. That is how vectors are defined, okay? Always the y components over the x component, and you're in business, okay? So this should be easy enough. The biggest work in here is actually getting this stuff done. Once you do that, the rest of the question is straightforward. In here, what you have problem 4 is that a small object with mass m, charge q, and an initial velocity v naught is equal to 6,000 meters per second is projected into a uniform electric field between two parallel plates of length 26 centimeters. And the electric field between the two plates is directed downward and has a magnitude of 600 Newton per Coulomb. Assume that the field is 0 outside the region, so there is no electric field. Between the plates, the separation between the plates is large enough for the object to pass between the plates without hitting the lower plate. So it must be a positive charge. It is. It has to be a positive charge, because if it's a negative charge, it's going to bend upward. So they will worry about the upward direction, okay? After passing through it, the object is deflected downward. So it's deflected downwards must be positive because the electric field is raining in, is going down. And the charge has to follow it then. In this case, the only charge that follows the electric field in this case is the positive charge. If it was bent up, then in this case, the charge is negative, okay? After passing through the field region, the object deflected downward by 1.15 centimeters from its original direction motion and reaches a collecting plate that is 56 centimeters from the edge of the parallel plates. Ignore gravity and air resistance. Great. If we have gravity, we have another. This is a projectile. Basically, this is what the problem is saying. Okay. You have an initial velocity v naught, and you have a region in here of electric field E, and the particle comes in with an initial velocity, and it's subject in that region to a force equal to QE. Okay. E is pointing down, so the force is pointing down. So instead of hitting the plate exactly with this velocity, if we neglect gravity and everything else, it's going to be bent because of this, and it's going to follow projectile. We're supposed to find this. They gave us this distance, actually. And from here, what was the question? So let's set up the problem first. This one is equal to ma. They gave us the mass. The acceleration is going to be simply QE over AM. So this is a projectile motion that you guys did in physics 4A. The only trouble with this projectile motion is only true up to this region, because from here, E is equal to 0. So from here, it's going to emerge with velocity that we need to know its direction, okay? That's it. So we have V naught on that direction. We have V on this direction. The x component, there is no acceleration, so the x direction is going to be governed by this equation, v naught t, and that is the x direction. And the y direction is going to be moving down from that direction by this acceleration, which is QEA over m times 1/2 times t squared. And there was no initial velocity in the x direction, in the y direction, and there was no, how should I put it? No. And I'm going to take the origin in here, okay? So this is basically the equation in the y direction, because it came through in the x-axis. So it has no components in the y direction. So it has no initial velocity in the y direction. So this is true only for up to x equals to L. Did they give us L? Yeah, 26 centimeters. For L equals to 26 centimeters. So for that time, it's going to reach it, L equal to V naught T, when it leaves, the time when it leaves this plate. So the time when it leaves that plate is given by this T, when it's left, is going to be L over V naught. So plug it in here, we're going to find how far it went down from here, okay? So that is y when it left. It's not going to be 0, it's going to be actually equal to this expression, 1/2 of QE over m times this time squared, which is L squared over V naught squared. So that gives us this time. I need to find this velocity though, the velocity at that point. The velocity in the x-axis is the same. It's not going to change. It's this value. But the velocity in the y direction is given by, the derivative of that expression, which is QE over MT. So when it leaves, it's going to have Vy when it's left the plates. It's going to be QE over M times L over V naught. So now this is the component of the velocity in the y direction, and it has already components in the, so I need to find its numerical value. I have L 26 centimeters. I have V naught 3000 basically meters per second. I have a Q, which is equal to, we don't know, so we're going to find it, okay? So we cannot use a number in here because we know where the impact is. So that is basically, so we know the velocity in here. It has this component V naught, which did not change, and it has this component which I just computed, and its direction is given by that one, and it's going to impact because it's uniform motion now at some point in here. Using the geometry that I have in here, I can find this distance of the impact. So by the time it reaches this point in here, now from this point on, it's uniform motion in both directions. It's both uniform motion in the x direction. It continues to be uniform all the way through, but it's going to be uniform motion from here to on. So from here, the velocity, the new velocity, if you like to call it, to start calling time a new time, where this is the origin. So the new velocity in the x direction is going to be the old velocity, which is basically, doesn't change at all because it's uniform motion in the x direction. But in here, this is the initial velocity and it's going to stay the same. From this point on, in the y direction, the y in the y direction is just going to be this velocity, QE over M L over V naught times the new time, where we're going to be measuring from this one, the t equal to 0. If I know this whole distance, which is 56 centimeters, I can find this time. So it will take 56 centimeters to travel, I'm going to convert it to meters, to travel this whole distance at the speed of V naught in the x-axis times the t. So it's going to take a time that I can measure distance over time. I can find that time when it hits this impact, plug it into this expression now, and I will find the additional distance it's going to travel in the y direction, because I can find the time for it going to 56 centimeters to reach the wall, and plug it into this expression. And now I have the y. Once I have the y, add it to the initial y because there was a y in here too. And now that must add up to, how much is it? D. And D is given 1.15 centimeters. From there, I should be able to find the value of Q because Q is unknown. Do you understand the problem? Forget about the algebra though. You understand that it's a projectile in here, in this section only. But then after that, it's two uniform motions in the x-axis and the y-axis. Yes?
Yes.
Okay. So basically, you have a bunch of equations. You need to find the times when it leaves the plate. That time is needed to find the velocity in the y direction. After it leaves, the velocity in the y direction stays the same, and the velocity in the x direction stays the same all the time. It doesn't change, okay? So you want to know how long does it take after it leaves to impact the wall. They gave you the distance, 56 centimeters. So you know the velocity, you can find the time. Once you have that time, you can plug it in the other expression. So basically, here is how the situation is. It started vertically, and it's supposed to hit the wall vertically if there was no electric field. Because of the electric field bending it, by the time it reaches this point, it has already traveled an initial displacement, which is given by this expression, because it's a projectile. So you need to find the time when it immediately leaves the plates. When it leaves the plates, it has displaced this amount in the y direction. In addition, to finding the velocity, because you need that velocity from this point on. It's a uniform motion down and a uniform motion also vertically. So now we know it's uniform motion. So by the time it's going to reach this point, there is an additional displacement, which you take from this expression to find t and plug it in this one because it's uniform, and you're done. And you found the, add the 2, and you should be able to find, it should be 1.5 centimeters. Okay, no problem, Marcella. So I assume that there is a little bit of algebra, but it should be, I mean, the physics of it is just you have two sections of motions. One which is a projectile, and the second one is two uniform motions. And you have a bunch of numbers to work with. Does this make sense?
Yes.
Okay.
Do you mind scrolling up a little bit on the diagram? I'm trying to. Okay, thank you. That's good. Sorry, I was just trying to map the diagram in my paper.
Okay. It's, I mean, I'm going to post it hopefully tonight. I mean, I know we are in already past an hour and a half, so it's going to be probably tomorrow morning before it's going to be ready. Okay. This problem 84. Okay. What this problem is, let me draw this problem quickly in here on the screen. I'm not going to draw it with color, so if you don't mind. I know that one of them is negative and the other one is positive. So what we have in here, we have semicircle of negative charge Q, uniformly distributed, and a positive charge on the other side that is sprinkled on the other side. Okay. So in here and in here. And they want to know, this distance is fixed, by the way, it's A, it doesn't change. And it's distributed, okay. So there is a uniform distribution on these arcs. One of them is a negative lambda, the other one is positive lambda. The only thing they have to remember is the circle is the radius 2 pi a, but you didn't sprinkle it on 2 pi a, you sprinkled it only on a quarter of that. So you sprinkled q over quarter of this number, which is pi over 2a. In other words, q, 2q over pi a is lambda. Does this make sense to you guys? You took q charge, one of them is positive and the other one is negative, and you sprinkled not on the entire ring, but only on a quarter ring. A ring radius is 2 pi a, but a quarter of that is 2 pi a over 4, or pi over 2a. Yes, I'm looking in there because that's actually where the other screen. Yes, makes sense?
Yes.
One of them is negative, the other one is positive. That's the only thing that you guys have to remember in here, okay? And then they start asking questions about the electric field and the direction, all of that. First of all, the direction is easy to do. So I would answer the second part first before answering the first part. So let me come in here.
What question?
Take an element.
Physics? Mastering physics?
Yes.
What
Problem
question?
84.
Oh, okay, thank you.
Okay, so I'm going to take an element ds in here, and I'm going to take a symmetrical element ds, meaning that they're sitting at the same angle, making a 90-degree angle, if you wish, in here, okay? So that whatever I argue for one by symmetry is going to be true for the other one. This is a negative, so the force is going to be pointing this way on it, okay? This is positive, so it's going to be repelling it. I'm sorry. Did I do it wrong? Controlling nonsense. Sorry about that. The negative pulls towards it. So this force is actually here. It's toward the negative charge. And this one is away from the positive charge. Does it make sense? One is negative, one is positive. The negative pulls towards it for the electric field. And this is the E plus from the other contribution. Yes or no?
Yes.
By symmetry, you can clearly see that the y component cancels. There is no y components, so the electric field must be in the x-axis, in the positive direction of the x-axis. Correct? So that answers the second question because it asks you for the direction of the electric field. Yes?
Yes.
So it's only a matter of finding the value now. And the value I will find 1 and multiplied by 2 and the end of the story. I'm done. Because they are equal in magnitude, but opposite in sign. And but I have to take the cosine, the cosine of this angle, if you wish. This angle I have to take its cosine to find its component in this direction. Because it's not just so E minus. I'm going to take an element of this charge, this charge, which is ds. So in this case, I have lambda ds in here. So the electric field is going to be K times, again, I'm using the notation K now, which is times lambda ds, which is the charge divided by the distance squared. The distance is fixed, a squared. And this is the magnitude of the electric field. Because the distance is fixed. As long as you are on that arc, the distance doesn't change at all. But I have to take its cosine of this angle. So I have to take cosine of theta now into account. So if I really want the electric field itself, it's going to be 2 because I'm going to project this one and that one, and it's 2 of them, 2k times lambda ds over a squared times cosine of theta. And this ds in an arc is like this. So what this theta is we start with theta is equal to 0. And once we integrate, we go all the way to theta equals to pi over 2, okay? And that is the integration. The boundaries of the integration is from 0 to pi over 2, but this is d theta, and this is ds. And the arc distance is related to the angular displacement by an equation that you saw in physics for A, where r is the radius, in this case, is equal to a. So the arc displacement is equal to actually a ds, I mean a d theta. That is the arc displacement. If you move just a d theta, that is the displacement on the arc. Okay. If you move 2 pi, it's 2 pi times the radius that gives you the whole circumference. Okay. So that's basically a setup for the problem. And I did the 2 in here because I already did the second part by symmetry. So I'm just going to integrate one of the integrals and give me by symmetry the other one. So E in this case is going to be the integral of 2k times lambda times ds, which is a d theta divided by a squared cosine theta, and the boundaries of integration are from 0 to pi over 2, and the a cancels the a, and now we're in business. So what is the integral of a cosine? That's a sine, isn't it? So E is equal to 2k lambda over a sine of theta evaluated between 0 and pi over 2, and this is just 1. Okay? Correct? The only thing I'm left with to do is replace the value because they didn't give us lambda, so we have to use the value for this lambda in terms of Q and A. It's 2q over pi a, and we're in business. So E is equal to 2k times 2q over a over pi a, I'm sorry. The whole thing is divided by a. I'm sorry, I already anticipated the answer in here because it has to have a distance squared in the denominator. So that's why I had put the squared in there. So this will be equal to 2 times 2, that's 4k. What is it? Q over pi a squared. Another way of writing this one is 1 over, what is it? Pi squared, a squared, epsilon naught times q. Because the 4 cancels the 4 in the 1 over 4 pi epsilon naught instead of writing it in k. So that's an alternative way of writing it. Make sense? If not, come back in here, look at this derivation and let me know if we need to elaborate more on it. Good?
Yes.
Okay, so the next question, 89. 2 small spheres, each carrying a net positive charge, are separated by 0.4 meters. You have been asked to perform a measurement that will allow you to determine the charge on its sphere. You set up a coordinate system with one sphere Q1 at the origin and the other sphere Q2 at 40 centimeters available to you. Our third charge with net charge Q3 is equal to 3 microcoulombs, basically, an apparatus that can accurately measure the location of this sphere and the net force on it. First, you place the third sphere at a distance 20 centimeter. You measure the net force, and it's 3.5 newtons in the positive x direction. Then you move the third charge to 60 centimeters and measure the net force on it, and the force is now.
Are you drawing anything, by the way?
So I'm not drawing. I'm just reading the problem. Positive x direction. So that's basically what the problem is saying. So basically what it is, let me use a different pen at least to. So basically what it is we have an origin charge in here, Q1, okay, at the origin, and 40 centimeters away from it, 40 centimeters, or yeah, 40 centimeters, 0.4 centimeters. This is Q2, okay? You don't know what these charges are. So what you do, you bring a third charge as you know its value. So Q3, you know it's going to be 3 microcoulombs, okay? And you place it first. You place it first at 20 centimeters. So you place it in here. This distance is known, 0.2 meters on it. And this is Q3, by the way. And you measure the force. You find the force on this one to be 3.5 newtons in the positive direction. So this is the force F on 3, which is 3.5 newtons as pointed in the positive direction, okay? And then you place this third charge in another setting. It's not the same. Q3 now is moved to another location now. So this is the first setup 1. Setup 2, you take Q3 and actually move it to another location. And this location is actually 60 centimeters. You place it in here now. So this distance is 40 centimeters, by the way. So now you place this charge Q at a distance of 0.6 meters. That's the same charge Q3. And now all of a sudden the force on it is just 2.5 newtons, and it's still in the positive direction. Somebody has a question? Okay, that's fine. Let's finish this hopefully quickly, and we should be going to. Because I know when it gets too long, it becomes kind of tiring a little bit, even though it's problems, which is not lecture. So let me set up the equations. We don't know what these forces are, but we know the force on Q3 in here is going to be coming from these two forces, from these two charges. So on one side, it's going to be this force coming from F2, which is going to be the distance is 0.4 deducted from it 0.2. So it's going to be 0.2, the distance. So this force of coming from 2 is going to be K times Q2 times Q3. And it's going to be potentially pointing in this direction, okay? If I assume Q2 to be positive, divided by, what is it? The distance squared, which is 0.2 squared, okay? Add to it another force from Q1 pointing in this direction, which is going to be plus K times Q1 times Q3 divided by, so this is a negative, that is positive, divided by 0.2 also squared, okay? So I have one equation involving these two guys. This must be equal to 3.5 newtons. When I placed it in here, this is pointing this way, and the other one potentially is pointing this way. So at this point, I don't know what the sign of Q1 is, and I don't know what the sign of Q2 is. So I'm going to leave them algebraic. So this expression is written algebraic. Potentially, both of them are positive. They may turn out to be negative, or one of them is positive, the other one is negative. Which one is which? The algebra will tell me. So at this point, I'm assuming both of them are positive. So the force on Q3 at this stage is 2.5 Newton. Is going to be equal to, again, K times Q1 times Q3 divided by this whole distance, and this whole distance is what? They said it's 0.6 meters, 0.6 meters squared, plus K times, again, Q2 over Q3, and this distance now is still 0.2 meters squared, okay? Solve these two equations for both Q1 and Q2, for Q1 and Q2 as unknown, and then you have your answer. Okay, calculate Q1, calculate Q2, and you're going to find the two values from here. But this is the setup for the problem. Okay, and then you place, they ask you which place you're going to place it so that's equal to 0 other than infinity. Since you know the two charges and you're going to place it somewhere in between them, so probably these two charges have the same sign then, or place them, and if they have opposite sign, one of them is repelling, the other one is pulling. So you have to find a suitable place for it. Okay, so here is the situation. If the two charges are of the same sign, this one, let's say for example, is repelling and the other one is repelling. If it's opposite, if the two charges are attracting, one of them is attracting this way, the other one is attracting that way, it's still there in the opposite direction. So there is a place in here where you can cancel the force. You need to find that one. So you call this distance x, and this distance is 0.4 minus x, and you solve for x. It's going to be a quadratic equation that's easy to solve. Or if the charges have different signs, then this one is, let's say for example, it's negative and this one is positive, then in this case, you can place the charge in here. This one is going to be repelled by it, and the other one is going to be attracted by it. So potentially they can cancel it there. If this charge is large enough to compensate for the distance. If it's not large enough to compensate for the distance, they don't cancel in there, but rather they cancel in here, where this one is weak enough but attracts it, and the other one is large enough but repels it just enough so that they cancel. So one or the other two will work for you if the charges happen to be of different size. If they happen to be in the same sign, it has to be in the middle, somewhere where the charge is going to be basically under no net forces, because one of them is pulling on it one way and the other one is pulling on it the other way, and they cancel. Okay. If they happen to have the same sign, I mean different signs, you can put it in the middle anywhere, because if you put it in the middle, one of them is let's say for example, this one is repelling it and the other one is going to be pulling it if it's a negative charge. And then it can never cancel in between if they're two different charges. And if they're the same sign, they cannot be canceling outside, cancel in the middle. Okay, so let's look at problem 7, the last one. A positive charge Q1 is 1.5 microcoulomb located at x equal to 0 and y is equal to 0.3 meters. A negative charge Q2 is negative 1.5 microcoulomb located at 0 and negative 3 meters. A third charge Q, 5 microcoulomb, is located at 4 meters, y centimeters. What is the magnitude of a charge on the charge? What is the magnitude of the electric force that Q1 and Q2 exert on Q? Okay, here is a problem. Let me draw it with another one, okay? So you have a charge in here and you have a charge in here, and they're sitting on the y-axis, and there's a third charge in here, Q. So this is Q1, this is Q2, they're by symmetry in there. So if these two charges, one of them is positive, the other one is negative, though you have to be careful in here. So the positive is on the top, so it's repelling it. The negative is on the bottom, and it's pulling on it. The two charges have the same magnitude, they're the same distance, so their x components cancel, but their y components add up. And you have to know the geometry in here. This distance is given to you 0.3 centimeters, 0.3 meters. This is 0.3 meters. And this whole distance is given to you being 0.4 meters. So this one is just using the Pythagorean theorem is going to be 0.5 meters. Okay. This is 0.5 meters because square root of 3 squared plus 4 squared is 5. Okay. So that's Pythagorean theorem. This is one of the triangles that they add up correctly in this case. So once I have the distances, I have the forces, I have the components of the force. I can find this force in here. I know by symmetry that this one is going to be 0 because the two charges are the same. Both of them are 1 microcoulomb each in magnitude. One of them is repelling, the other one is pulling though. So in the x-axis they cancel, but in the y-axis they contribute. So I have to add the sine of this angle, which is the sine of this angle, which is equal to 0.3 over 5, twice. Make sense?
Yes.
Okay, so we went through the entire deal. I didn't know we can do that, but we did. And it's been about 2 hours. Wow. You guys survived it. I'm sorry to take you through this whole thing. Okay, so I'm gonna post this one hopefully tonight. It's 2 hours, most likely it's gonna be tomorrow morning. Any questions? Andrea, were you saying something?
I was just gonna say thank you for doing this. It was very helpful.
No problem. No
Sorry,
problem.
I had my
Super.
button just like on the mute and unmute, just like waiting for the right moment to speak.
Problem.
But yeah, thank you. It was helpful to see the problems broken down.
Okay, very good. How about you, Caesar?
Yeah, this cleared up a lot. I appreciate you doing this.
Okay, no problem. Yusuf, Drake, Ron, Gonzalo, Torres.
I joined in a little late, so I'm probably going to be watching the recording on repeat tomorrow morning, but this was a very helpful video. Thank you very much.
I don't know if you watched the problem 94, but that was really a doozy problem. So I'm going to go back and probably have to adjust the grade for it because it's really
Yeah,
it's
I
not easy.
think I joined in halfway on that one, and oh boy,
Yeah.
I've been there at the beginning, huh?
Okay. Yeah, that was kind of.
Also, I want to say it's funny because the thing says estimated time 2 hours, but the first problem took almost an hour for
Yeah,
us to do.
the problem. I have to adjust it. Okay.
Okay.
Okay. How about you, Yusuf? Do you have any question for me, or Ron, or Torres?
I was personally wondering where we could find the recordings, in case we missed things.
Okay. The way my classes are structured, all classes, okay, we usually have, at least for the calc base, we have a review of the terms that are used, and then what is it, the recording immediately after that. Let me look at the structure in here again. It's usually in the chat session, in the discussion session. Every module, what is this one? This is not your class. Let me look at it in here. So every week we have at least two things. We have an overview of the concept to be covered, and then we have a chapter discussion where you're supposed to, you're required to do an assignment there. It's going to be there in the discussion session. Now this one is a special one. So it's going to be in its own discussion session without a grade. Okay, it's going to be on this week because we did it this week, week 2, unit 2. So I'm going to create a session for it, and it's not going to be graded, but you're going to find the recording in there. And that's basically how to watch for these things. Basically, every week, as far as the lecture is concerned or the lab is concerned, we record it, we put it there, and it's going to be found in there. Because this one is kind of long, so I know it's going to take forever to download on my computer. And I know that it's going to take a million years, probably not exactly a million years, but maybe very long to upload back to YouTube and fix whatever. Sometimes the sound comes weird, so I have to fix that. And upload the link to Canvas, and hopefully you guys will have it ready by tomorrow morning. Okay?
Okay.
Okay.
Thank you.
Yusuf, do you have any question? No problem. Yusuf.
No, I don't have any questions. We're good.
Okay, very good. Okay, so I'm going to stop the recording now, and I will see you guys next week. And have a nice weekend, okay?